everybody. Welcome to the first lecture that I am recording for our course on natural language processing. This is the first lecture that I've recorded. It doesn't have to be the first one that you're watching, right? My intent is that as you are thinking about and working on your class project, that you're going to let that kind of guide what material you need to be accessing, right? And what lectures you need to be watching. So you don't have to watch these lectures in order. It's fine if you choose to, but just because this is lecture number 1, don't think that this is the first one you have to be watching. The content for today's lecture is going to come from chapter 2 of our textbook, which is Speech and Language Processing. And again, you don't need to be reading along, right? It's very important that you are getting the material out of the textbook, that you are reading the textbook, but let your own needs and your own interests and your own availability in your schedule define kind of how you're using the textbook, how you're using these lectures, right? So I will be using the slide deck provided with this textbook, as today we talk about regular expressions. So regular expressions are extremely important in computer science and in NLP specifically, right? They're really kind of part of every single task in natural language processing. They're extremely useful. It's an extremely broad skill to have. They are also very unpopular and one of the biggest nuisances in computer science, honestly. They're one of those pain points for a lot of students because they can be kind of finicky and they can be kind of hard to remember. And so my advice is that you not try to memorize regular expressions too much, right? There's a lot of good information out there. Google them when you need them, right? Ask ChatGPT to write a regular expression for you when you need to. You do not necessarily need to memorize everything about regular expressions, right? Instead, know where you can find good information about them, right? And our textbook is one of those good sources. And we're going to look at some other good sources for Python documentation a little bit later in this lecture when we're doing our code demonstration. But don't feel like you have to memorize everything about regular expressions, but don't shut them out of your consciousness either. They're extremely important. You need to have them around. So let's imagine I have a hobby. Right? Let's imagine I really like woodchucks, and I want to be able to find information about woodchucks, right? So I want to be able to search websites to find occurrences of people and articles talking about woodchucks. Well, that's easy, right? I get my little web search and I type in the word woodchuck like we see here, and boom, I search and I find every occurrence of the word woodchuck. Little w, little o, little d, little c, little h, little u, little c, little k. Okay, and that's good, right? Now I've fed my hobby. But it's possible I'm missing a lot of occurrences, right? Since natural language doesn't follow rigid and repeated structures, right? And this is going to be a theme that we see a lot in this class, that since natural language evolved organically, right, it doesn't always follow rules like we want a mathematical language to, right, or a programming language to, right? So if I just search for woodchuck, if I find every occurrence of the word woodchuck, little w, right, I'm going to miss a lot of interesting information to myself, right? For instance, if someone was talking about woodchucks, plural, well, that doesn't match my first string. Or if woodchuck appears at the beginning of a sentence with a capital W, well, that doesn't perfectly match my search string, right? Or, since I'm such a woodchuck enthusiast, I know that woodchucks are also referred to as groundhogs. And so if I just search for woodchuck, I'm going to miss all of the occurrences of groundhog, right? And then this word groundhog is going to have all of the same troubles with pluralization and capitalization that woodchuck did, right? So I've got one concept that I'm interested in, right? But what I really want to search for isn't just one string like woodchuck, but instead a whole family of strings, right? A whole related group of strings. So regular expressions are a way to define families of strings, groups of strings, right? We might say that they're a formal language for specifying strings, or the way I like to think about it is that they're like a meta string, right? It's like the metadata that lets you build a family of related strings, strings that share some property. So let's start looking at how we would make one of these regular expressions, right? And perhaps this is something you've seen in classes before, right? As I said, regular expressions are extremely important to computer science, so hopefully this isn't the first time you're using them, but they're very important in natural language processing since we necessarily do a lot of string parsing, string searching, string splitting, right? Regular expressions are very important to us, where we're going to start off just from the foundations, learning how to craft regular expressions. And one of the most basic tools we have available to us is a disjunction, these square brackets, right? A square bracket means that I want an exclusive OR of the characters that I put in these brackets, right? We're going to match one and only one of the characters in the brackets, right? So if I open up a set of square brackets here, and I type in a little w and a big W, and then I just finish woodchuck normally, the way I would normally type that string. Well, now what I have is a regular expression that implies two strings, right? From this expression, I can build two strings, either woodchuck capital W or woodchuck little w. Both of these strings are in a family of strings defined by this regular expression, right? Or imagine I just want to find a digit somewhere in a document, right? So I might open up my disjunction, my square brackets, right, and type out 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Now, this family of strings is just any single digit, right? Since square bracket means pick one and only one character from inside of these square brackets, right? And something y'all are going to notice right away is that typing out 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 is kind of a pain in the butt, right? So what we can instead do is define a range using a single dash like this, right? So big A dash big Z means, right, this is a disjunction that matches any one uppercase letter, right? So if I say, hey, I'm searching for this pattern, right, this regular expression, right, and I'm searching in this string, drenched blossoms, which we see in the top row of the bottom table, right, that pattern is going to match on that first character, right, a capital D, right, since that satisfies the conditions of our regular expression, which is just the range big A to big Z. All right, or I could use little a to little z, right, which matches any lowercase character. In the second row of this table, my beans were impatient is the example string, and so we match on that first little m. That is the first character that satisfies the pattern that we've defined in this regular expression, right? Or 0-9 will match with any one digit, and will do so a little bit more gracefully than typing out 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Right, so something you're going to notice is that we're starting to use some logical operations, but we're applying them to strings rather than to Boolean variables or to logical values, right? So it's very natural for us to think that, okay, if I can match a pattern positively, right, can I say, yes, this character is in this range? Well, can I negate that? And yes, we absolutely can. And we do that with a caret, which is the little upward pointing arrow. You might be used to using this for like exponentiation in some cases, right? So the up caret there means not, right? So up caret big A dash big Z is a regular expression that matches anything that is not an uppercase character, right? So if we give it the name Oyfin Pripachik, right, the first character of that string that satisfies our pattern is the little y, right? That is the first character of the string that is not an uppercase character, right? Or if we look at the second row of this table, caret big S little s, well, that's going to match any one character that is not a big S or not a big S, or I should say nor a little s. Right? So notice here, this caret, this negation, this not applies to every character that is inside of this bracket, right? So this isn't just not big S or yes, little s. This is not big S nor not big S, or not little s, sorry. So the first character in the string, I have no exquisite reason, that satisfies our pattern is the capital I, right? Okay, so we might also negate just a single period. This is significant because in regular expressions, a period is a special character. We're going to talk a little bit more about these special characters in a slide or two, right? But one that you might be familiar with is splat, the asterisk here, right? This is a normal wildcard in many fields of computer science, right? Typically this wildcard, this asterisk, matches any character, right? Well, these special characters kind of lose their powers when they're inside of square brackets like this. So if I do something like not period, even though period is a special character in regular expressions, right, it loses its power, right? It becomes just a pattern that is not a period. We also want to notice here in the last row of this table that this caret has a particular order, right? This caret is specifically a prefix operator, right? So e caret becomes a pattern that matches either a little e or the character caret itself, right? Caret here has lost its special powers. It is no longer a logical not because it's got no characters after it. So we're going to find with regular expressions that there are some that we look for a lot. So for instance, any digit, right? Or any alphanumeric, or any white space, right? And many of these are built into, for instance, Python's string processing tools, right? So like isAlpha or isAlnum are built into that language, and so that gives us kind of an indicator that that's a really important thing to do, right? But let's look at what it takes to write out a regular expression that matches any alphanumeric, for instance, right? So that is one character that can be either a little character, so A through Z, or a big character, A through Z, or 0 through 9, right? So the third row shows us that to match any alphanumeric, I would have to type out inside of my square brackets little a dash little z, big A dash big Z, 0 dash 9, and if we throw in an underscore, it'll match an underscore too. And I don't have time for that, right? That's not something we want to type out repeatedly over and over and over again, right? And we've also seen in coding, right, since all of you have probably been through software engineering at this point, that retyping just invites mistakes, right? It's much, much safer to figure something out once and then reuse it as many times as possible. So for instance, by putting code in a function to improve its reusability. Right, so instead of typing out here in the third row, A-Z, 0 9 every time I want to match any alphanumeric, regular expressions, many regular expressions, right, support aliases. And I say many because regular expressions are not necessarily universal. There are a lot of conventions that are universally agreed on, for instance, square bracket disjunction. But aliases like this kind of gets supported sometimes and not supported other times. So be careful using these, but use them when you can because they're convenient, they're useful, they prevent mistakes, and they save your time. Right? So aliases are just shortened versions of a square bracket disjunction. Right, so we type that with a backslash followed by a single character. Backslash is the funny one that lives up over your enter or return key. If you use Mac or Linux, you probably only use backslash as like the trap character for putting like new lines into a string, for instance, if you're doing some string processing in a program. If you use Windows regularly, you use this slash in your file paths quite a bit. So you know where to find it on the keyboard. The rest of you will find it above your enter or return key. So slash little d will match any digit, slash big D will match any non-digit, slash little w will match any alphanumeric, slash big W, right? And notice the pattern here negates, because slash big W matches any non-alphanumeric, S will match white space and big S will match non-white space. Cool. Aliases. Alright, so far we've been writing disjunctions that match a single character, right? Which is great for some things. For instance, if I want to search for little w woodchuck or big W woodchuck, right? If I want to account for capitalization. But imagine that I want to match entire words. Right? If I want to define a disjunction of entire words, for instance, groundhog or woodchuck. Well, I can do that with the pipe symbol, the single vertical bar. All right, that means either match the left side or the right side. All right, so if I define the pattern groundhog, pipe, woodchuck, that would match woodchuck, or that would match groundhog. It would not match groundchuck or woodhog, right? It has to perfectly match one string or the other on the left or on the right. So yours, pipe, mine matches yours. It matches mine. It doesn't match any other combination of those letters. A pipe can take more than two inputs, right? So here A pipe B pipe C is the exact same as square bracket ABC. And we can use those square brackets within the pipe, right? So if I, for instance, define a pattern, little g or big G round hog, pipe, little w or big W woodchuck, well, that would match big W woodchuck, little g groundhog, or big G groundhog. All right, those special characters we were talking about, right? We all know that an asterisk matches any character, right? I don't know exactly where that convention started. It definitely applies in like bash scripting for any of y'all who have learned how to do that. Our wildcards are going to work a little bit different in regular expressions, right? Since sometimes we want patterns to be able to repeat, right? And so we can use some of our special characters to show repeating patterns. So our special characters are as follows. A period matches any character. So beg.in would match begin, begun, beg 3 in, beg space in, beg plus in, beg d in, right? Any character can stand in for that period, but it has to be a single character, right? We might also want to say that a character is optional, right? That it does or does not appear. So for instance, we might want to match woodchuck or woodchucks, right? We might want to optionally pluralize a word. So a question mark shows that the preceding character is optional. So woodchucks question mark matches either woodchuck or woodchucks. The asterisk in regular expressions, or splat as I normally call it, means that the previous character appears 0 or more times. So to splat matches t or two or two or two or two. Right? You can insert any number of O's and it will still match the pattern. And notice here that no O's also satisfies that splat pattern, right? That asterisk pattern. Sometimes we want at least one of the preceding characters to exist, right? So the plus sign means that one or more of the preceding characters will show up in the pattern. So TO plus matches TO, TOO, TOOO, TOOOO, but not just a T by itself, right? So TO plus, notice, is equivalent to TOO asterisk. And so sometimes we also want to be able to specify where in a string our pattern occurs, right? So for instance, we might want to check to see if a string starts with a capital character, right? Which might indicate to us that it's a proper noun, right? And that's going to be very important to us later on in this class when we start talking about named entities. So, we can use anchors, which is either a caret or a $sign, to represent the beginning or end of a string, right? So caret bracket A through Z is a pattern which matches any string that begins with a capital letter, right? So for instance, Palo Alto satisfies the pattern caret bracket big A dash big Z. Or we might say, hey, any string that does not start with a letter, be it capital or otherwise, so that would be caret bracket caret A through Z, A through Z, right? So caret here has more than one job, right? It does a different job depending on if it's inside or outside of a square bracket, right? If it's inside of a square bracket, it is the not character. If it's outside of a square bracket, it indicates the beginning of a string. It is an anchor, right? Likewise, the $sign stands in as the end of a string. So if we want to find, I don't know, any sentence that ends with a period, we might use, let's look at this bottom row, period $sign. Well, except we're being told that that matches the end question mark or the end exclamation point. And what's gone wrong there? Period is a wild card for us. Period matches any character, right? So period $sign is any string that ends with a character, right? So the end and the end both satisfy this pattern. Our third row in this table, though, slash period $sign. Now, since we're using that slash, we're referring to a literal period, not the special character period. And so now only the end matches. So regex is very well supported in Python. But since I know you've all worked in Python before, since you've all taken our Intro to AI class, well, you know that backslash is used in Python strings for inserting special characters. For instance, \n is a new line in a Python string, and honestly in all C family language strings that I know of. So if we want to put a backslash into a string, we actually need to insert 2 backslashes. That's a slight pain in the butt. So what you can do instead is use raw strings in Python, right? This is a string where the little r character precedes the opening quotation marks for that string, right? We're all familiar, or at least should be familiar, with F strings in Python. F strings mean apply special formatting. R strings, raw strings, mean don't apply any sort of formatting. R strings ignore backslash characters. So the R string /D plus would be a regular expression that matches one or more digits, and that just saves you the trouble of having to type \D plus. So how do we get these regexes? How do we get these regular expressions, right? Well, we really need to start with an understanding of what it is we're trying to find, what it is we're trying to match, right? So really we need to start with like a problem we're trying to address. So for instance, find me all the instances of the word the in a text, right? So, okay, here's a search string written in red on our top example here. The, just the word the. Let's just search for the word the. right? But just like we saw with woodchucks and groundhogs earlier, this is going to miss a lot of examples of the word the, right? Since it's going to ignore capitalization. So okay, let's allow for capitalization. All right, let's use a square bracket disjunction. Let's say it can be a little t or a big T. It has to be followed by HE. And now we're going to find every single occurrence of the in our text, whether it starts with a lowercase or capital T. And we're also going to find every occurrence of the word theology, since the characters THE appear in that string, right? And it wouldn't really be appropriate for us to anchor, right? We can't use our caret or our dollar sign here, since we don't know if the is going to occur as the beginning or the end of a string, right? So we need instead some way to indicate that this word stands alone. The is by itself. So let's say white space, then the, then white space, right? And so now we would find every occurrence of the word the in the text, right? And let's think about the process that we followed to do that, right? Since, well, we started off with a guess, right? We started off with our first search pattern, which was just the by itself, right? And then we encountered one type of error, right? We found a false negative, right? A type 1 error, right? Essentially, we realized that our search string was ignoring legitimate occurrences of the word the, and in specific, it was ignoring capitalized occurrences, right? Okay, cool, so we fixed that. Then we noticed that we were getting some false positives. Any string that contains the word, the characters THE, was also matching our search pattern, right? Where we use the disjunction with the little t or big T, right? So for instance, there satisfies our search pattern, then, other, theology, right? So that would be an occurrence of false positives, type 2 errors. So defining a correct regular expression first starts with knowing the problem you're trying to address, and then identifying the errors, right? And refining your process, right? So eliminating both your false positives and your false negatives are how you start with a problem, move to a guess, and then refine that guess until you're getting correct behavior from your regular expression. So regular expressions are extremely important. They are widely used both in academia, right? So you're going to use these in classes. You're going to use them in this class fairly regularly. And they're useful in industry. These are an employable skill, and they're one that not many people focus on because they can be frustrating. So take your time, read your textbook, look for your other good sources on the internet, learn regular expressions, learn how to use them, learn how to apply them. They will be your friend. All right, let's move on and see what regular expressions look like in application. Okay, so here we are ready to apply some of the knowledge we just learned from our slides, that we just earned from our slides. So I've got my coding environment up and running here. I like to work in notebooks. Notebooks are very common in AI and data science right now. And I like to use Google Collaboratory for this, because why use your own compute resources if you don't have to, right? Notebooks give you a lot of portability and a lot of convenience. But if you want to code along in your own VS Code or your own PyCharm, we're just using Python today, right? So any environment that you're comfortable with will work, right? As long as you're on at least Python, like, let's say 3.10. Okay, so today we're going to be looking at the regular expression library in Python, right? So that is just RE. I can go ahead and import that, and boom, I've got it. And I've prepared for us, for our first problem here, a simple file, right? And I can blow this up a little bit if y'all really want to see it. It's not super important, right? This is just the history section of the Wikipedia article about regular expressions, I have separated every sentence into its own line, right? So all of the sentences are separated by new lines now. I've removed most of the citations. I see one still hanging out here, right? And this is just to give us some convenient text to search, because I want to start off with finding every mention of regular expressions in our sample text. And let's see if we can figure out how many of them there are. Okay, cool. So we need to be able to read this file from this notebook. Most of y'all may know how to do this already, right? But since this is the first lecture, even if it's not necessarily the first lecture you're watching, right? This is the first one I'm recording. I'm just going to jump into the Files tab over here on the left. I'm going to upload to session storage this exact file, which I just happen to have on my computer. All right, cool. So now we've got 27 lines of text that I have borrowed from Wikipedia, and we are ready to start reading this. Awesome. So I'm going to use a file context to go ahead and start reading my file. So with open as F. All right, so for the open function here, I need to put in my file path to this file. All right, the easiest way to do that is just to copy the path, and then I can Control-C it in over here. Boom, there we go. All right, so this seems to be pretty consistent, right? That this temporary storage is always accessed as /content. I don't know if that's going to be universally true in Google Collaboratory, so that's why I always use the copy path instead of trying to type it out by hand. All right, let's just lines is equal to f.read lines. And I'm going to give that a quick print just to make sure we actually read something out of our file. Oh, look at that. Cool, cool, cool. So most of y'all should know that really using like open and read or read lines is not the optimal way to read a file in Python, right? Especially if it's something like JSON or CSV or like an XLSX, right? A file with an implied structure to it. Since this is just TXT, right, and this is just a simple demonstration, we're going to go ahead and use open and read lines. But in general, if you need to read a large data set or a large corpus, it's better to use, for instance, pandas to read the file. Okay, cool. So we've got all of our lines. And now let's just iterate over it. So for line in lines, I want to print every line that mentions regular expressions. Okay, so y'all can see my tabs up here, right? And if y'all know anything about me as a programmer, you know that I never code without documentation. I never code without at least a few tabs open. So I've got my documentation for the Python regular expressions module sitting over here, right? And what I like to do is just jump around and find myself, some example code. Oh yeah, okay, yeah, match, okay. And there's search. Oh, and there's full match. Okay, cool. So it looks like we've got 3 functions that we could be using. Match looks for a match at the beginning of a string. So that's not super useful. Search matches anywhere in the string. And full match means that the 2 strings have to match exactly. Okay, cool. So it sounds to me like search is the tool that we need to use. And I see here in the usage of search that I provide a search pattern, which can be a regular expression or is a regular expression. And then on the right is going to be the string that we're searching. Okay, cool, cool, cool. So let's say if re.search, if I see regular expression in line, and here line is just the name of this local variable that I'm using to iterate over my list of strings, lines. So if this is true, let's go ahead and print line. Else we will do nothing at all. Let's see. So if I run this, oh, cool. All right. So here we go. Other early implementations. Okay, there's regular expressions. That did appear. Okay. Regular expressions, it's in there. Regular expressions. Awesome. Yes, it looks like we have correctly selected some sentences that contain the phrase regular expressions. Right? But we saw from our iterative process, right, those last couple of slides, that this is just the start, right? So let's start thinking about what we could be missing. So for instance, it could be little r or big R. Right, so let's give that a run. Oh, and now it looks like we got a couple more. Yeah, since this first one here starts with regular expressions, right? And I could also, if I'm really feeling like a completionist today, search for little e or big E. I don't think that's going to change anything, right? Since it's impossible for expressions to be at the start of the string. Okay. And let's think some more. You know what? Sometimes regular expressions are referred to as regex, R-E-G-E-X. I think we even saw that in the slides. And if we look at some of this text and we dig around, I bet we're going to find, here, regex. This is actually regexes. Okay, cool. So let's use now, since we're matching a whole phrase, let's use a pipe to define regex. Okay. Oh, look at that. We did get some more. And so notice here we're kind of getting the plural for free, since the string regex is actually in the string regexes. Cool. And of course, that could also be at the beginning of a sentence. All right, so here we go. We have found a fair number of sentences that contain regular expressions or regex. All right. I'm not seeing any occurrences of regex appearing as part of a bigger string, so I don't think we have any false positives, right? If we were just searching, for instance, for regular, I think we would be getting some false positives, but by specifying the entire phrase there, regular expressions, we don't seem to be getting any false positives. So, a question lingers here. How many are there? So, I could, give myself a variable and increment that variable there. Since this is Python, let's go ahead and try to set this up using a list comprehension, right? So instead of iterating over lines, I'm going to define a new list, regex lines is equal to, let's say line for line in lines. All right, and now my condition can still apply. I just need to replace that colon with a closing bracket. And now what we want to know is the length of this new list that we've just made. So let's print the length of that list. And it looks like we have found 14 lines out of the 27 that originally existed in that file contain regular expression. I just noticed I made this plural. That probably doesn't need to be plural. Let's see if it changes if I make that S optional. Look at that. We caught 2 more. There we go. So it looks like we have 16 lines in total. I encourage you to run this code on your own. If you want to run it, you would just need to look up the Wikipedia article for regular expressions and copy and paste that into a text file and let me know if you get a different answer. All right, but this was kind of a toy example. Now, let's try something a little bit more serious, right? Let's try email validation. Let's let our user type an email address. I hope you all remember the input function in Python. Let's practice our spelling and put an R in your. There we go. Okay, and so what I want to do is check to see if this email is valid. Email is valid. I'm going to print valid. Otherwise, I'm going to print invalid. Right? And in the real world, you would probably want to, like, do something like force them to retype a password or something. Right? We're just going to use an if-else today. Right? But validation is important because as programmers, we never, ever, ever trust our users, right? Users are just the least trustworthy people on the planet. All right, so not a valid email address. There we go. Cool. So all we need to do is figure out how we can do this, right? Since Python is a friendly language, but it won't quite fill this in for me. So I want to use pattern matching to fill in something here, right? I'm going to define some search pattern. I'm going to compare it to the user's email. If I satisfy this condition, so if our pattern matches this string, I'm going to print valid. Otherwise, we will print not a valid email address. Okay, cool. So let's run this just to make sure everything is working. Let's type bob@bob.com. Okay. Our empty search pattern does appear in the string. That is true because, right, an empty string is a subset of every string, right, or a substring of every string. So our search pattern is in this email address. Huh. Okay. Well, let's just make sure that we can reject email addresses. All right, so let's try searching for exactly bob@bob.com. Okay, bob@bob.com. If I search that, okay, that works. But if I type just Bob by itself, okay, cool, not a valid email address. Okay, cool. So the if-else works. We just need to keep refining this pattern, right? So let's think about what makes an email address valid, right? And it's going to kind of come down to 3 chunks separated by known characters, right? I need to have some characters, then @ then some characters, then dot, then some characters, and nothing else. Okay. So let's see if this works. Bob@bob.com. Oop, I mashed a bad character when I ran that. So let's run that again. Bob@bob.com. Oh dear. Okay. What have I done? Okay, cool. So, yeah. We need to refine this a little farther, right? Since we've got some bad behavior, right? So we know what an email address should look like, right? So, well, it can be any characters, right? So I can use a range for that. Okay. Or it could be any characters. Okay. And actually, you're allowed to have numbers in your email address too. So let's add that to our range. Oh, that should be 9. There we go. And actually, you can have dashes in your email address as well, right? So this dash, we have to put it at the end so that it won't think that it's part of a range. All right, and I'm gonna just snip this out real quick so that we can test with a little modularity, right? So, okay, if I type Bob, okay, so that's accepted. Okay, Bob at bob.com. Okay, 123.123.123. Okay, cool. All right, so now we know that the next thing we need to plug in is what can go in this middle range, right? So that's the domain that we're trying to address. And that's actually pretty similar, right? So, okay, let's grab that and drop that in. Okay. And then the domain, okay, let's grab that and drop that in. And actually, it's acceptable for email addresses to have subdomains too, so there could potentially be another dot there. All right, cool. So let's give this a try. Let's say Bob at bob.com is accepted as valid. And it's Google even recognizes this as a valid address because this has become an interactable link now. Okay, just Bob by itself, not a valid email address. Awesome. 123 at 123. Oh dear. So it's accepting that. So why was this accepted? Let's walk through this and do a little bit of debugging. And something I'm noticing is, oh, right, this period is a special character, right? So this actually just matches any character. So let's replace that with a literal period. And let's run that again. 123 at 123. Not a valid email address. 123 at 456.com. So this appears as not a valid email address. Oh, right, of course, because each one of these brackets is only a single character. So let's say that actually this needs to repeat. So I can use wildcards for that. Or special characters, right, since these aren't behaving like our normal wildcards. And let's actually think about how that's going to behave, right? So for instance, if I type at and dot, that now shows up as a valid address since this repetition is 0 or more. And what we actually want is 1 or more characters. 1 or more characters. 1 or more characters. Okay, so let's try that. At dot should be not valid, and it is not valid. Okay, 123 at 456 should be not valid, and it is not valid. 123 at 456.com is valid. Wonderful. Okay, so now my only concern left is what if we type an address like this, bob at bob.com. It still shows up as valid even though I typed all of this extra junk in front of it, right? So we kind of want to specify that no, we have to start with this pattern. So let's go ahead and throw in a caret. And similarly, we don't want a bunch of junk after the address. So let's throw in our anchors. Let's say it has to start with this pattern and there can't be anything after this pattern. The string has to terminate after this pattern. So let's try bob at bob.com. Still works. Extra stuff before bob at bob.com, right? And notice This doesn't match our pattern because white space is not part of this disjunction, right? If I were to put a blank space in there, this would match, but that's not what we want. So I'm going to ignore that. And I think we now have a good regular expression that matches a valid email address. So that is the demonstration I've prepared for today. Thank you for your attention. I will see you in our class sessions, and I will see you in our later lectures.